The topic is memory management, and it is in continuation to other videos, part 1 and part 2. In this video, we'll be studying contiguous memory allocation and non-contiguous memory allocation. So when you talk about schemes, memory allocation schemes, we can have memory allocation for uniprogramming operating systems or multi-programming operating systems. But as you all know that we use RAM and we load different types of processes in the RAM. So we'll be having multi-programming as we want to utilize maximum CPU. So this uniprogramming we are discarding, and we are discussing in detail the multi-programming memory allocation schemes. So under this we have contiguous and non-contiguous memory, that what is contiguous and what is non-contiguous. Contiguous memory allocation means when the process is not divided and stored continuously in memory block, in single memory block in the memory. And whereas non-contiguous memory allocation means the process is divided and stored in different blocks which are available that time in the memory. So main difference between contiguous and non-contiguous memory allocation is the division of a process. Here the process is not divided, but here the process is divided and stored at different locations in the memory. So first we will be discussing the contiguous memory allocation in this PPT, in this video. So under this we have two types of contiguous memory allocation. First is fixed size partitioning and second is the variable size partitioning. Likewise in non-contiguous we will be discussing paging, segmentation and the scheme which uses both this paging and segmentation. So let's start with fixed size partitioning and variable size partitioning under the heading contiguous memory allocation, where the process is not divided and stored continuously in the memory. So as it is of two types, the process is not divided and there is contiguous memory allocation, continuous memory allocation. So this diagram demonstrates the fixed size partitioning diagram, and this is variable size partitioning. These are the short forms. FSP means fixed size partitioning and this WSP means variable size partitioning. So let's see, in this RAM the portion is divided, some portion like 40K is divided or allocated for the operating system, and rest is partitioned. This memory is partitioned for different types of processes to be stored here. So if request is there like P1, P2, P3, and P1 request 40K space, P2 20K space, and P3 40K space. So whatever scheduling algorithm you are following, suppose we follow here FCFS, that is first come first serve. So we'll allocate P1 first, then P2, and then P3. So as you can see, this RAM structure is having fixed size of partitions here. All the partitions, all the uh, spaces or the parts of the RAM are of same size, that is of 40K. So same size means this is fixed size partitioning scheme. So processes are loaded as they were arrived like P1, P2 and P3. But the problem is like P1 requires full 40K space, so this 40K space is allocated to P1. But in case of P2, it only requires 20K, but the partition size is 40K in RAM, so this 20K gets wasted, and this is the drawback of this fixed size partitioning. This is known as the internal fragmentation problem. Likewise, if we talk about variable size partitioning, so initially in variable size partitioning scheme, there are only two partitions. First is allocated for OS only, and the rest is uh, not divided. As soon as the processes arrive, the memory is divided according to the demand of the processes. Like this memory is not divided initially, but when the process P1 arrived, 40K is allocated to it. When process P2 arrived, 20K is allocated to it. When P3 is arrived, 40K is allocated to it. But the problem is when the memory is left in this manner, when another process arrives, if we do not have the sufficient memory, then it leads to external fragmentation problem. So this continuous memory allocation has a problem of fragmentation. And in the last video, we have also seen that compaction is the solution to this problem, but this compaction cannot be used every time. So better solution to this problem is that we move on to other types of memory allocation scheme, that is non-contiguous memory allocation. So in non-contiguous memory allocation, we will divide the process and we will store wherever we find the memory available in the RAM. We will store the process in that particular block wherever the memory is free in RAM. So non-contiguous memory allocation, the process is divided into number of parts, and these parts in logical memory are known as pages, and the partitions of RAM where we'll store these pages are known as frames. So this is very important to remember and understand that pages is the term which is related to logical memory. When you talk about loading of pages into RAM, then these pages are loaded into frames of the RAM. These partitions of RAM are known as frames. But when you talk about the CPU addressing allocation of these processes, then the process is divided into pages. So CPU divides the process into pages, and these pages are loaded into the frames in main memory. And also the size of page should be equal to the size of frame. Like here in this diagram, we have divided the memory into 40K size pages, and this is also fixed partition scheme where we have fixed size partitions, fixed size frames in RAM. So the size of page is equal to size of frame. For example, process P1 is divided into three pages, like for example page 0, page 1 and page 2, and all these pages are of same size, that is 40K each. So we will load the process P1 into RAM having 40K frames, 40K size frames. So this process P1 when divided into three pages is loaded wherever we get the free space, like page 0, the first part of process P1 is loaded here, second part of process P1 is loaded here, and third part of process P1 is loaded here. So process is divided and loaded into the RAM, and this process is divided into the first, it is divided into the pages, and these pages are loaded in the RAM in the different frames. But the problem is, how do we come to know that where my page number such so and so is loaded in the RAM? Because it is random, wherever we get a space the page is loaded. So the solution for this problem is page table. So this page table stores the page number and the corresponding frame number to know the position of each page in the memory. Suppose this process P1 is divided into three pages, page 0, page 1 and page 2, and this is the structure of RAM where we have loaded these pages. So in frame 0 we have loaded the page 0, in frame 2 we have loaded the page 1, in frame 3 we have loaded the page 2. So this page table is a part of memory management unit which stores the page number as well as the frame number. So for page 0 of process P1, it is showing the location where we have stored it in the RAM, like it is showing this in frame 0, and likewise for page number 1 of process P1 the location is frame 2 of RAM, and for page number 2 of process P1 the location is frame 3 of RAM. This scheme is known as paging. This is known as paging in non-contiguous memory allocation. So the fixed size partitioning in contiguous memory allocation was used long ago, but it is the basis of the evaluation of different memory allocation schemes. So we discussed that, but uh, we found some problems in contiguous memory allocation. So we moved to non-contiguous memory allocation, and under non-contiguous memory allocation we have seen this scheme. This is known as paging. So it is a memory allocation scheme in which the physical memory allocated to a process is non-contiguous. Physical memory is divided into fixed size blocks called frames, and logical memory is divided into fixed size blocks called pages. And also the size of each page should be equal to size of each. Also, I would like to tell you about some registers which you will study in the books. It is LBR and UBR. LBR is the lower bound register and UBR is the upper bound register. This LBR is also known as base register, and this UBR is also known as limit registers. So these two terms you will find in your books. These are nothing very simple. Base register is the minimum address any CPU can allocate to a process, and limit register is the maximum address any CPU can allocate to a process. So process address should not be less than LBR and it should not be more than UBR. It should always be in between LBR and UBR. If this is not followed, then the interrupt is generated and the process gets terminated. So the addressing by CPU should between base register and limit register. So in the next video, we'll be discussing non-contiguous memory in detail with more examples of paging and segmentation and the combination of both paging and segmentation. Thank you.